Do you have any questions about previous lectures? Uh, okay, so let's continue the last topic. So let's talk about different examples of the Fourier transform. So we have already seen this example that 1 over p plus I gamma for gamma greater than 0 corresponded to the following function. Minus I Heaviside theta of minus x e to gamma gamma x. And this was an example of a function that was decaying too slowly at infinity, and this caused discontinuity in its Fourier image. But by the way, we can notice another thing. If we go in the opposite direction, we see that this function is very nice in a sense. It's analytic, infinitely differential, and even analytic. And this corresponds to a function that decays at infinity with a very fast rate. And the rate of its decay is defined by the closest singularity of this function, the closest singularity to the real line. So and it's a general phenomenon. If you can extend your function analytically into some strip, in a sense that there is some analytic function that sticks on the real line like your function, then its Fourier transform will decay at least exponentially at infinity. So let us study what happens if we take another function which is decaying with faster rate. So, namely, let us take two such functions and cancel their asymptotics at infinity. So let us take 1 over p plus I gamma minus 1 over p minus I gamma. Again, gamma is greater than 0. So, can you try to guess what the Fourier transform of this function is?
Maybe we can extend x to negative x.
So, in a sense, there is such a component, but so we can write. So definitely, this argument about closing the contour works. Still works for negative x, right? So now we have two singularities. Minus I gamma, that was here originally, and plus I gamma. So now you have two options to close the contour either in this direction for one values of x or in that direction. So one of the answers will be the same. In a sense, it still contains this component. So we will have minus I theta heaviside of minus x e to gamma x. But there will be also another component that should remove discontinuity of this function at 0. And we know that this component will contain an exponential with the opposite argument, because it will be a contribution from another pole. Right? So, what should we write here? What other function can it be?
I, a side of x,
Mm-hmm.
e to
Yes, thanks. No, it should be with a minus sign because they should coincide at 0, right? Yes. So we see that this function is decaying exponential for both values of x, and we can write it shortly as e is minus I e to minus gamma x, absolute value of x, right? So we can also simplify this function, writing it with a common denominator. So we can write it as 1 over p squared plus gamma squared minus 2 minus 2i gamma. So the statement that we have here is the following. That if you cancel this 2 and I, then we have a statement that integral dp from minus infinity to plus infinity 1 over pi gamma over p squared plus gamma squared is equal to e to minus gamma absolute value of x, right? So it's an important integral, and it or its relatives will appear many times in different contexts. So let us study this a little bit. Sorry, I forgot to write the Fourier transform IPX here. So we have such an integral, and let us study, for example, what happens if we put x equal to 0. So one cover of this formula is the following. So, and this is a function that we have already seen when we try to compute direct and then inverse Fourier transform. So, this is what we call the delta gamma of p. So, we can indeed check that the integral of this function equals to 1. And this is a delta-like function in the sense that it has width height of gamma and width of also height of 1 over gamma. Its value at 0 and width of approximately gamma. Of course, this integral can be computed as the integral as definite integral of this function, it equals to some arctangent, and then we need to specify it to plus and minus infinity. But in most cases, indefinite integrals are easier to compute using methods from complex analysis, because it's a typical situation that we can compute some integral with infinite limits, but its analog for finite limits, for fixed limits, is not expressible in terms of algebraic or some generalizations of algebraic functions. So it's a typical method to compute such integrals from minus to plus infinity. Yeah. So we have this integral, and maybe for now that's enough for examples. And I wrote this to be able to use this result in the following computations. So now let's switch to the example, to a problem of about the inverse Fourier transform. So we define Fourier coefficients of function f by f and tildes equal to d phi over pi e to minus I and phi f phi from 0 to 2 pi. And we need to check that if we take so defined coefficients and take Fourier series with the same coefficients, we will recover our function. Overall integer numbers. So let us simply take those integral representations for coefficients and insert there. So but actually, before this, let us do one more thing. Let us first check that if we modify coefficients of this Fourier series with a cutoff function, then the result of this sum will be close to the original function. So, namely, let us first prove the following statement, that if we introduce f hat of phi, which is equal to sum over integer n's, gamma maybe let us call this f gamma. Yeah, like this. So so we consider such a function. We also need one more requirement on the coefficients of its Fourier series. In a sense, we say that. Yeah, let me introduce such a notation. Yes, it's needed. Uh, Sum of absolute values of its Fourier coefficients is less than infinity. In a sense, it's convergent. So if it is true, then supremum over the whole circle of absolute value between of difference between modified function gamma of phi and unmodified function 0 uh, goes to 0. Well, limit of when gamma goes to 0. So I'm saying the following: if you have a set of Fourier coefficients that decay sufficiently fast, so that the Fourier series is absolutely convergent, then adding such a regularization with the exponential cutoff will not change the result in the coordinate space. And so it's easy to check. So namely, we can say that this absolute value of difference, gamma of phi minus f 0 of phi, is a sum of absolute value of fn. So then let us write that this is less or equal than this sum from sum between some cutoffs in the space of integer numbers. So will be sum from minus n to n. That will be adjusted in the appropriate way. Plus sum over absolute value of n greater than n of epsilon. And this gamma will also be a function of epsilon. So
You're truncating the series, but you're saying it's less than the full series. You're truncating the series because now you want to going over all z.
No, but I'm saying that this is less or equal than sum of absolute values of two parts.
Oh, sorry, you're breaking it
Yeah.
down. Okay.
Mm, mm,
Classic triangle psychology.
yes. So now we can simplify these two parts in two different ways. Uh, Here we can choose the maximal value of this difference of cutoffs, and here we can simply replace this cutoff function by 1. Yeah. Both operations will increase each of these parts. So here we can write that it is 1 minus e2 minus gamma uh, gamma n of epsilon uh, sum from absolute value of n less or equal than n of epsilon. Plus and let me introduce the dependence of gamma of epsilon here. Mm. And here we can also remove all these exponential prefactors and write a sum of absolute values like this. Mm. It's not equal. It's this is greater or equal than the first part. Uh, so uh, uh, now, and by the way, we can also do the same here. So well, it doesn't matter. Mm, So here we know that this is less or equal than infinity. It is some number which is restricted by some value. Less or equal than some value. And now we know that this series is convergent. So if we adjust the cutoff n, it can be made arbitrarily small. So we can make this less or equal than epsilon over 2. This means this comes from convergence. And here we can adjust the value of gamma, so that this prefactor is also less or equal than epsilon over 2. In a sense, we should choose gamma arbitrarily small. So we can make this less or equal, so less than epsilon over 2a. So after all, we prove that this can be made less than epsilon by appropriate choice of gamma, right? So, so it's fine, right? Right? Or so I'm saying that if we had a function that behaved well at infinity, well in this sense, then we can add another regulator which simplifies our life when we start computing the inverse Fourier transform. And now let us compute this f hat gamma. So it equals to sum over integer numbers e to I and phi, integral from 0 to 2 pi d prime over 2 pi minus, well, let's put this regulator here, gamma absolute value of n. So we can move this integral outside because the sum is well convergent. We can write it as integral from 0 to 2 pi d phi prime over 2 pi times sum over integers e2 minus gamma absolute value of n plus I n phi minus phi prime f of phi prime. So let's take care of this sum. We can denote it as delta S1 gamma of phi minus phi prime. And so let us terminate this computation for a while and try to compute this sum and study its behavior. So this delta S1 gamma of x is sum over minus gamma absolute value of n plus e plus I n x. Oh, it can be written as a sum from n equals to 0 to infinity e to minus gamma. Let me write it like this: minus gamma n minus gamma minus ix times n. Plus sum from n equals to 1 to infinity e to minus gamma plus ix, I suppose, n. So they are both decaying with n, but this decay has different origins. So let's compute these sums. So do you know the value of the first sum? Yes. So what does it equal to? Yes. And what about the other sum? So
Same plus ix in
uh,
parentheses.
yes, and also it starts from 1, so we should have the same thing in the numerator. Yeah. So we have e to minus gamma uh, uh, plus ix over 1 minus e to minus gamma plus ix. Yeah, so we have some expression. Uh,
Do we say that gamma minus ix and gamma plus ix should be in module minus of 1?
oh, what
No, sorry. Gamma minus ix is
so we need to check the absolute value of the whole argument, and so gamma is positive, so that this function is decaying with n, and the absolute value of the second exponential is just 1 because x is real. It's from 0 to 2 pi. Yeah. So yeah. Let us look at this function for gamma equals to 0 and x different from 0. So x different from 0, uh, limit of gamma goes to 0 of this function. So it is 1 over 1 minus e to ix plus uh, e to minus ix over 1 minus e to minus ix. So we can divide by this exponential and get the following. So this is 0, right? So this is what we could expect if it was a delta function. So we know that the limit of this function from 0 to 2 pi, so it goes to 0 here. By the way, x is not only 0, it should not be in the set 2 pi times integers, because this exponential is periodic in x. Yeah. Now let's study what happens if x is close to 0, and gamma also goes to 0. Well, in this case, we can expand each exponential as a series in gamma and x. 1 over gamma minus ix plus 1 over gamma plus ix. So I write it like this. So this equals to gamma over gamma squared plus x squared. So comparing to our delta-like sequence, it looks like 2 pi times delta delta gamma of x. So this is delta function on the real line. So we can say that this delta function that we obtain here, so the same happens at all other points. So we can say that this function delta gamma on s1 of x behaves when gamma goes to 0. It behaves like sum over integers delta gamma in the real line x minus 2 pi n times 2 pi. So the port of this function has this form: 0 at 2 pi, so on at minus 2 pi, and something like 2 pi over gamma, approximately. So let me check the coding. And let me actually check the free space on the phone that it doesn't interrupt. Okay, so we have this kind of statement, and so we can resume our computation of the integral. We can say that it equals to integral from 0 to 2 pi d phi prime over 2 pi 2 pi. Well, let me cancel this 2 pi here and there. No, well, let me keep it. D phi prime over 2 pi. See? F of phi prime. So, as long as we have this expression for the asymptotics of our delta function on a circle around 0, we can use it for computation of this integral. So we know in particular that if we substitute x equal to gamma 1/3, then this function is also of order gamma 1/3. Delta of gamma to 1/3 is gamma 1 all of gamma 1/3. So we can split this integral into two parts. We can write that it is an integral from well, actually, since everything is periodic, we can write it as minus pi to pi. Maybe it's easier. So we can write this integral as integral from minus pi to minus gamma plus minus gamma to 1/3 d phi prime not pi. So let me write another part of integral from gamma 1/3 to pi d phi prime over 2 pi we have this part plus another integral from uh, minus gamma to 1/3 to gamma to 1/3 phi prime, so phi prime, phi minus phi prime. Okay. I I wanted. Sorry, I forgot this shift in shift by phi. This is sum from phi minus phi prime, and so here we should also shift in integration domain by phi. Phi, and here as well. So we are splitting this integral into two parts. One part that includes the domain where our delta function behaves as a delta function, and another domain when it goes to 0. And now I want to say that this integral is of order gamma to 1/3, because this gamma function is of order gamma to 1/3, and everything else is finite. So this is and this integral, if f so d phi prime over 2 pi, and this integral, as long as f is smooth enough, it can be approximated by f of phi times this integral from phi minus gamma to 1/3 to phi plus gamma to 1/3 delta gamma s1 of phi minus phi prime d phi prime over 2 pi plus plus some all of gamma to 1/3. And this integral can be extended to plus infinity, again with some corrections, so think of the same order. So it will give us f of phi plus plus all of gamma to 1/3. So we see that the limit of f hat gamma when gamma goes to 0 is f of phi. So maybe better to say that this is a uniform limit. So we can write that limit of supremum of the absolute value of f of phi minus f at gamma of phi from phi from 0 to pi equals to 0. So it means that the Fourier transform of our function converges uniformly to the original function. So, so it converges with the regulator gamma, but we can further show that its partial sums also converge. It is easy. So so we can conclude that f of phi equals to this sum. So other questions? Let us also study a convergence of partial sums, right? I can probably erase this delta sequence here. So we have f ends of phi that equal to sum from n from minus n to n. We can compute the difference of f of phi minus f n tilde of phi. We know that the full sum will give us our function point-wise, and we want to compare this difference for this difference with a partial sum. So it equals to absolute value of sum over absolute value of n greater than n e to n phi f n tilde. And this can be restricted by sum over the same domain, absolute value of n greater than n, simply of absolute values of n tilde. And if we are in the assumptions of this lemma, then this sum is convergent, and this goes to zero. Goes to zero when n goes to zero. And of course, it goes to zero uniformly because it's this estimation does not depend on phi. So if you are in that that situation, then we have this. And now, what about another convergence? So this can be called probably L infinity. It is called this way. We can also check the L2 convergence. Namely, let us compute the absolute value squared of this difference of functions. So f of phi minus fn of phi, f of phi minus fn of phi. So this will be the difference. This will be the same series, but with some part of its coefficients removed. So it will be sum over absolute value of n greater than n f tilde n squared. So we know that this is convergent for continuous function. So this series goes to zero. Yeah. So are there any questions about this?
So the expression sums of the Fourier series converges if is continuous, converges always in L2, but if it's only continuous, it's not factored, then converges
Yes. And
but if it's C1, then
uh, yes, actually there is the assumption is not that straight. It also works for continuous functions, but proof of this is more complicated. It uses some other techniques. So the Browner transfer, for example, just refer to some more general theorem that is not proved there. But here I decided to do everything elementary, but under a little bit stronger assumptions. But you see that if we formulate it in terms of behavior of Fourier coefficients, then we can distinguish between good and bad cases. So, so if you know that this sum is convergent, then everything works, and we can construct counterexample when this uniform convergence breaks. And this is what I'm going to show now. Mm. So, are there any other questions? Mm. Okay, so let us consider a function that has an explicit jump. The simplest example of this function is this. So there's 0, pi, and let this function be 1 from 0 to pi, and minus 1 from pi to pi, or from pi to 0. So we see that there is one of those problems with the uniform conversion that it's simply impossible to realize because this function is not very well defined at 0 and pi. We can define it as 0 as 0 at that point, but this does not help because if you try to draw a continuous function and all the partial sums are continuous, so they will not converge to to our original function. Uh, So actually, one would expect something naive, like that this function can behave like this. Uh, uh, I don't know. I understand that the only problem would be at 0, but actually it's not the case. I'm going to show that the actual behavior of this partial sums that approximate our function is this. Uh, so and this is called Gibbs phenomenon. Yeah, but first of all, this counterexample is not just another theorem, but an opportunity to compute a Fourier transform of some function on a circle to see how this works. Mm. So let us try computing coefficients of the Fourier expansion of this function. So they equal to integral from 0 to pi, or maybe let us better write as integral from minus pi to pi, because everything is periodic. E to minus sine phi times f of phi, d phi over to pi. So it equals to integral from 0 to 2 pi, from 0 to pi, e to minus sine phi, d phi over to pi, minus integral from minus pi to 0, e to minus sine phi, d phi over 2 pi. So we'll compute it as the integral from of the exponential. So it is 1 over minus in times 2 pi e to minus sin pi minus 1 right here minus 1 over integral 1 minus n pi in 2 pi 1 minus e to in pi. Right? So let us look at this carefully. So there are minus 1s that don't cancel. And there are minus 1 to the n that also don't cancel. Right? So these terms are equal. And all this can be written as 1 over I n pi 1 minus 1 to the n. Right. So this is something that cancels for even n's and equals to 2 over n pi for odd n's. So we can write our partial sum as sum over n that equal to 2k plus 1. K is integer. E to I 2k plus 1 phi 2 over n pi I write it as 2 over I 2k plus 1 pi. And now we can combine positive and negative parts of the sum into a single sign. So it equals from to sum from k equals to 0 to infinity 4 over 2k plus 1 sine of 2k plus 1 phi. So it was f. We are interested in partial sums. So let us add a restriction of k by n. So and this sum will be from k equals to 0 to n. So this is such a function. And you can check that if we put phi equal to 0 identity, then it's 0. It's fine. what if phi is small? So hmm, we want to study small positive and small negative of phi because our original function behaved like this. So we want to study this and this region. We want to see this phenomenon. Mm. So we need to compute the sum somehow. So since phi is small, we can neglect discrete structure of the sum around zero, but there will be many other contributions for a very big case. So this sign is small when its argument is small. But if small phi times some big number of the sign kinds of order something like phi over 2, then the sign starts contributing. So we can write this sum as we can approximate the sum by integral. So we can first write that it was a sum in k for delta k over k plus 1 sine of 2k plus 1 phi. But so it can be approximated by integral in uh, let us write it actually like this. Let us multiply delta k times phi over 2k plus 1 times phi. So it's identical transformation, but I want to say that the new integration, the actual new integration variable will be k times phi, or 2k plus 1 times phi. So we can. Hmm? So far it is just 1. So we can approximate this integral by the following expression. So it is 4 dk dk times phi over 2k plus 1 phi sine of k plus 1 phi. So this integral is in k. But it's natural to choose the new variable. And so let us say that the new variable to k plus 2k phi plus phi is called x. And phi is small. And k should be big, so that we have non-trivial contributions in this integral. Well, this phi goes to 0, and we can approximate it like this. And the upper limit of integration in this new variable will equal to 2n times phi. So there will be integral from 0 to 2n times phi of 2 dx over x times sine of x. Right. So it's the actual integration variable, and if you look at this comparison between sum and integral, then this partial sums, when phi goes to zero, represent a kind of Riemann sums for this integral with discretization given by phi. So we change of k by 1, shift this x by phi, and phi goes to 0. So when phi goes to 0, we can do like this. So we can say, we can write it slightly differently, that it is an integral from 0 to n phi to integral of sine of x over x dx. If I remember correctly, it's called the sinc function. Of 2 and phi. So if by the way, I should turn on the light. So the integral of sine of x over x, and so let us draw sine of x over x. It starts from 1. It has a finite limit, and then oscillates like this. And if you draw the value of its integral, then you see that it has a non-zero derivative at 0, because this function equals to 1. But then it starts oscillating. Within, maybe it's and so on. So it has a maximum when its derivative equals to 0. So this point is equal to pi over 2 when when no, sorry, this point is pi when sine vanishes, and this is minus pi. So this maximum is at point pi, and this is at minus pi. So since this function depends on 2n times phi, then position of this maximum in this picture should be what? It should be pi over 2n. So this is pi over 2n. So this function will have maximum that goes to 0 with this rate. So if you take it at any fixed point and consider the limit and goes to 0, then of course it will converge to the original step function. But if study if this convergence is uniform, then the answer is no, because there will always be a point where it has a value different from the limiting value. And mm, mm, and by the way, let's compute the value of this function. Oh, sorry, probably I missed some factor of pi here. Yes, I missed the factor of pi. Mm, yeah, here and here and here and, and here. So is it fine? Uh, let's check that this limiting function actually converges to what we want. Mm. Uh, So to do this, we need to see what happens when n goes to infinity. When 2 and 5 goes to infinity. So it should be 2 over pi. Mm. 2 over pi. So I want to study this because it's another nice example of application of residues for computation of such integrals from 0 to infinity or from minus to plus infinity. So we want to compute the integral from minus infinity to plus infinity of function sine of x over x. Let us call it I. So if you want to express this function in terms of this integral, then it is 1 over pi times times the integral. Mm. So mm, uh, uh, maybe I should move to another blackboard, probably here. So I want to compute this integral. Uh, we see that in principle it could have singularity at 0, but since sine of x over x has a limit, there is no singularity. But anyway, let us remove a small part of the real axis just in case. So it's in the same integral because function had a limit. We can write a limit epsilon goes to 0. Mm. But once we write it like this, we can say that sine of x is an imaginary part of the corresponding exponential. So it is limit for epsilon goes to 0, uh, imaginary part of the integral from minus infinity to minus epsilon plus integral from epsilon to infinity to ix over x dx. So now let's draw a picture. There is a real line with this interval removed. And this is precisely the position of pole. So what? And we know that if we close the contour, we will be able to use a residue theorem. So do you have any suggestions for computation of this integral? What should we do to apply the residue theorem?
In like quantum field theory classes, when we have residues on a line, we would protect them off the axis.
But here it's not the case, because we had this integral from the very beginning, and residues are no, in a sense you can do this, but no, you actually cannot do this because your contour is not closed. So. Oh, let me think if it was possible from the very beginning. Yes, actually it was possible from the very beginning to, we could move this pole to the complex domain, but I chosen another way. Yes. So, and the answer would be the same, of course. So, all right. So, yes, we can add this small half pass here, and another integral at infinity. So we can call this C0 and this C infinity. So we know that if you take all of them together, we will get 0, but a sole combination of these three integrals is a 0. So the integral over the real line is minus the integral over contour C0. C0 e to I x over x dx. Imaginary part. And since it's half contour, it's a semicircle, then this integral equals not to minus 2 pi I, but just to minus pi I. So it is minus imaginary part of minus pi I. So equals to pi, right? But indeed, we could compute this integral for the shifted pole. The only problem is that we would need to close contour for two different terms in two different ways. One would give 0, another would give the residue, but the answer would be the same. Yeah, but doing this way, we get this integral is equal to pi. So if we go back, then what is the value of this function? So it's 2 times half integral. So it's the origin. It's the whole integral divided by pi. So it equals to 1. As it should be. So you see that if you integrate this function to infinity, multiply by 2 over pi, then we get 1. So the asymptotic value of this series, or in other words, the limit when we keep phi fixed and send n to infinity, well, phi fixed and close to 0 and to infinity, then it's indeed 1 and minus 1. So, yeah. So this is how this discontinuity looks like.
How did you do that the integral over the minus c infinity contour was 0 also?
Because this exponential goes to 0. It is e to I times imaginary number with big imaginary part. And the only points we should take care of are these points close to the real line, because the imaginary part is 0, but in those cases we have denominator 1 over x. So they go to 0, prefactor in front of the exponential goes to 0, and integral of the exponential is fixed, so it's finite. It's concentrated in some finite domain of the real line. In a sense, we are evaluating something like integral from 0 to infinity of in dy e to minus y plus I r minus over r plus iy. Yes, this can be estimated by absolute value of this integral can be estimated by 1 over r integral from 0 to infinity e to minus y dy. So this is 1. This contribution comes from this domain. So and this is minus r, and this is r. The problems would appear if this function was of order 1 at infinity. And this actually happens if you consider some periodic functions, for example. Okay, are there any questions about this? So, let me now tell a little bit about this phenomenon that we observed here, that there were some functions that appeared as integrals with usual functions, and we had some kind of convergence of such an integral with a well-behaved function f of phi. So it's a part of general construction, which is called generalized functions. And delta function is an example of such functions. So generalized functions are a dual space, so, elements of the dual space two infinitely differentiable functions on, for example, R, but we can put S1, for example, or some other manifold. Uh, and if it is R, then this infinitely differentiable functions should have a compact support. Hmm?
We usually denote with a C, not a zero.
But this?
Yes,
Okay.
we denote with zero the function that vanishes at infinity.
But compact support means that they vanish at infinity.
Yes, but
Okay.
there are functions that vanishes at infinity,
Mhm.
which doesn't have
Yes.
compact
Yes.
support.
Yes, it's true. But, to be honest, such functions are also fine in the context of generalized functions. In the sense of this compact support is used only to define the space, but all expressions that appear in reality contain functions with, which are much less restricted. So, mm, uh, have you already learned about generalized functions in some of the courses, or not?
We have done, we came from a different university, so
Ah,
we don't know what they have done in the University of Trieste.
I see.
We've seen definition that wasn't very formal. We had an idea
Yeah.
of what is this, but
Ah,
we don't know how to manage the
mm.
function.
I see. So hopefully I can tell something new about them. Maybe no. Let us see. Yeah. So uh, 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 so it means that there elements of a space of a linear space that can be paired with such functions. So f a generalized function phi is in the compact of R. This is some complex number. Is always row defined. Uh, examples of generalized functions. Mm. So first of all, there are usual L1 functions that can simply be integrated with the generalized function, and maybe not even a one. Let us take some continuous function. It should be enough. Maybe even it can be even less restricted. Uh, hmm. So if it is just a function, this pairing can be defined as the integral from. So pairing with phi is defined as the integral from minus infinity to plus infinity f of x, phi of x. And there are other examples, namely, we can take, let us write something, let us put here delta. There is clearly there is a linear function on the space that simply takes the value of our function at 0. We can also define another function which we call minus delta prime that takes the value of its derivative at 0. Or delta 2 primes and that takes second derivative of phi. And of course, it can be they can be taken at any other point. So maybe can erase this. And we can define with convergence. So we can say that f1 converges to f1 psi1 converges to 2f1 0 if for any phi find a test function from this nice set. F1 epsilon with phi converges to F1 0 with phi. And as you saw from our computations, this with convergence was everything we needed for practical reasons. In a sense, we could use we could use elements of sequence of functions that were normal functions to perform this computation, to pair them with phi, and then take a limit that produces precisely expression like this, phi of 0 or phi prime of 0. So, and the computation we did, oh, sorry, actually this, it was this blackboard. It was proved that delta-like sequence was actually a delta-like sequence. So, so actually could have removed F. So it's a equivalent definition. So So there is this convergence, and what we already checked, and we can look at this again. Um, so remark, this could be usual functions. So example of this phenomenon. Uh, this expression 1 over pi epsilon over x squared plus epsilon squared converges to delta of x when epsilon goes to 0. Proof of the statement. We can write that the integral of dx from minus infinity to plus infinity phi of x times 1 over pi epsilon over x squared plus epsilon squared is sum of two integrals. Integral for absolute value of x less than epsilon to 1/3 dx phi of x 1 over pi right. So we can now replace this function by phi of 0, saying that the difference, oh, we can write many triangular inequalities, and let us actually try to do this. Yeah, so we can write that it equals to integral for value of x as an epsilon to 1/3 dx phi of 0. we can write it like this. And since phi is C infinity function, we can check. So it's some boring computation. Probably we should adjust some behaviors. No, but probably it's enough. So we can prove that all these terms go to zero for, you see, infinity functions, and then this integral goes actually to phi of 0 when epsilon goes to 0. So this way we can check that the limit of pairing of this delta-like sequence with any function f, delta epsilon with any function phi is indeed phi, so converges to phi of 0. Therefore, this delta sequence actually converges to a delta function. And in, so as we saw, in practical cases, it is much easier to work originally with delta sequence and then take the limit at the very end. So maybe. And of course, we had this question, like, what are the equations satisfied by the green function? The answer is this. That equation has delta function on the right-hand side. Delta function is the generalization of delta chronica to the continuous case. So it appears precisely at those places where we had delta chronicas. So, okay. Do we have any questions? So also one more remark that since we have such definitions, then we can perform Fourier transform of a generalized function, because a value of the exponential value of its derivative at 0 is a well-defined object. We could put here e to IPX. So.
If you integrate a function against the derivative of the delta function, you get the derivative of the function at that point.
No, so, it's a minus derivative of the delta function because we need to integrate by parts. Okay, thanks for your attention.